Introductory Chemistry, Chapter 10, Chemical Bonding, Lesson 2. So in the last lesson, we looked at how do we draw Lewis structures for covalent compounds. So we're going to use those Lewis structures to determine their shapes. Why do we care about the shape of molecules? Well, it's important in determining properties relative to each other. So for example, what might have a higher boiling point or melting point? Can these two compounds mix together? Which one might have a higher surface tension or higher viscosity or higher vapor pressure? So the shapes and looking at whether a molecule is polar or not gives us a lot of information about certain properties. So we're going to use the VSEPR theory to determine the shape. And VSEPR stands for valence shell electron pair repulsion. So we're talking about our valence shell electrons and the fact that they are going to repel each other. The repulsion is greater between lone pairs of electrons than what it is between bonded pairs of electrons. And so then we can get our shapes and bond angles from this. So looking at things that have less than an octet first, beryllium hydride. Beryllium can only make 2 bonds. We look here, we see that this is a linear structure with a 180-degree bond angle. Boron trifluoride forms 3 bonds, right? Boron is left with only 6 electrons. And this shape is going to be trigonal planar with a 120-degree angle separating the fluorine atoms. So what happens when we have a full octet? Well, when all of the electron pairs are bonded to our central atom, we see a tetrahedral shape. And we can represent this on pen and paper by drawing normal lines that are in the plane of the paper, a dashed line that goes behind the paper, and a solid wedge line that is coming out in front of the paper. So in a tetrahedral shape, no lone pairs, our bond angles will be 109.5 degrees between each of our hydrogens. So what happens if we have 1 lone pair or 2 lone pairs? So basically we look and we're seeing, hey, this looks a lot like the previous slide with methane, except for now nitrogen doesn't have this extra bond. Instead, it has a lone pair of electrons. So your electron pair geometry is still tetrahedral, but when you have 3 bonds and 1 lone pair, our shape is now trigonal pyramidal, and our bond angle is 107 degrees. Still basic electron geometry of tetrahedral when looking at the water molecule, but now we've replaced 2 of the bonds with 2 lone pairs. So that gives us an angular or bent shape. And our lone pairs are up here, which are actually pushing these bonded pairs of electrons closer together with the hydrogens, so that we see then our bond angle decreases even more to 104.5 degrees. So here's one example of a shape table, and I gave you a shape sheet in class and you have one in your book. In terms of once we draw our Lewis structure, we have to figure out whether or not we have lone pairs or not, and then we're doing a total count. How many bonded atoms are there? How many lone pairs of electrons are there? And that is going to directly relate to your molecular structure as well as your bond angle. So we do our counts and we look at our table and we would see that 2 plus 2 equals 4 total pairs gives us a bent molecule. So my suggestion with this slide is to hit pause, draw your Lewis structures, and then come back to the slide and see if you got your answers correct in terms of what are the molecular shapes. So as you have drawn out these structures, we're making sure that we're paying attention to the number of lone pairs of electrons and the number of bonded atoms on each of our central atoms. That's what we care about. So in determining our molecular geometry, when I draw nitrogen trichloride, I'll see that I have 1 lone pair on the nitrogen and I have 3 bonds, 3 bonded pairs to chlorine. So that gives me trigonal pyramidal with 107-degree bond angle. Sulfur dioxide is going to result in a lone pair of electrons on the sulfur. We've got 2 bonded atoms, so that's a 2 plus 1 is 3. This gives us a bent shape, and our bond angles would be less than 120 degrees because of that lone pair. So your electron arrangement is trigonal planar, but that lone pair on sulfur pushes those oxygens a little closer together. Phosphorus trihydride is similar in structure to nitrogen trichloride. Phosphorus is going to have a lone pair of electrons, single bonds to each hydrogen, which results in a 1 plus 3 is 4. So that tells me my shape is trigonal pyramidal, and my bond angle is about 107 degrees. In silicon tetrahydride, this is similar in shape to methane, which is CH4. So silicon has no lone pairs. It has a single bond to each of these hydrogens, which results in a tetrahedral shape with bond angles of 109.5. And then lastly here, looking at selenic acid, selenium's in the center with 2 lone pairs of electrons. It has 2 bonds singly to each hydrogen atom, resulting in a 2 plus 2 equals 4. I look at my shape sheet and I see that the shape would be bent, and my bond angles are 104.5. I cannot stress enough to you that you have to draw your Lewis structures before you can figure out your molecular geometry or your shape. And you need to be able to find your shape, because then the shape is going to lead to whether or not a molecule is polar or nonpolar. So how can we figure out whether a molecule is polar or nonpolar? Well, we use what's called electronegativity. And electronegativity is an atom's attraction to electrons in a bond. So we can think about this as almost like a tug of war between electrons, or between atoms, where the electrons are being pulled on. So the atom with a higher electronegativity is stronger and will attract those electrons to it more in a particular bond. So high electronegativities exist for nonmetals because we know that they want those electrons. Low electronegativities for metals because we know metals would like to give up electrons. This is how we become stable. So when we have elements that have similar electronegativities, then we see this competition for electrons. And within the competition, it's determining the extent of our bond polarity. So let's take a look at the table that shows us our electronegativities. As we can see here, our electronegativities are increasing from top to bottom and left to right across the periodic table. So my highest electronegativity is with fluorine, which is a value of 4. My lowest electronegativity is with francium, which is 0.7. So in order to determine the polarity of a bond, all you do is look at your atoms and subtract. The difference between fluorine and hydrogen, 4 minus 2.1 is 1.9. The difference between phosphorus and lithium is 1.1. That tells you electronegativity difference. So then how can we classify our bond types? Well, we just talked about how do we find our electronegativity differences. You subtract. You look at the numbers and you subtract them. So when our electronegativity difference is less than 0.4, we say it's nonpolar. If it's between 0.4 and 2, we say it's polar. And if it's greater than 2, we classify it as ionic. But there is a sliding scale for something that is truly nonpolar to become polar, that is more like ionic, and then completely ionic. So that's what this little graph up here is showing. Compounds that are truly nonpolar, which would have an electronegativity difference of 0, up to those that have an electronegativity difference of greater than 2, right up here. So as we have talked about before, ionic compounds form between metals and nonmetals. Metal, nonmetal, metal, nonmetal, metal, nonmetal. So we can see that what we've said about this holds true. Down here, we have electronegativity differences less than 1. So we have our hydrochloric acid, hydrobromic acid that are slightly polar. And then we get increasingly less polar as we get to a diatomic chlorine. So polar covalent bonding, what does it look like? Because fluorine has an electronegativity of 4 and hydrogen is 2.1, we noted that the difference was 1.9. So this is a very polar bond here, almost ionic in nature. So we say that this is slightly positively charged, sigma plus, and over here we have a sigma minus. So what are we looking at? That this is sort of negative because it's pulling the electrons towards it. So a truly covalent bond can only occur when both atoms are identical. Polar covalent, right, is happening here because we have electronegativity differences. Fluorine's tugging on hydrogen's electrons. This is important too because we notice here this is an acid. Well, why are acids readily able to give up their H's in a reaction? It's because the atom that it's bonded to is already holding the electrons closer to it, so then the H can just leave as an H plus and it's just happy to do that. So it helps to describe our behavior of acids as well. So Lewis structures and polarity. So in looking at a polar bond, we know that that has to be an electronegativity difference of 0.4 to 2. This results in what we call a dipole moment. And a dipole moment is drawn down here, and it's showing that you're going to draw the positive end of this arrow by the positive end of your bond, which is the less electronegative atom. The direction it's pointing is going towards the more electronegative atom. So this is slightly negative over here. So slightly negative atom, slightly positive atom. These are basically vectors. And you can add up your vectors and see if there is an overall dipole moment. So when we have an overall dipole moment, we have a polar molecule. If we do not have an overall dipole moment, then we have a nonpolar molecule. So it's just basically thinking once again about the tug of war. And if we're pulling in equal and opposite directions, then nobody wins the game, right? But if one team is stronger than the other, then somebody wins. Polar is when there's a difference. Nonpolar is when there isn't. So how can we determine polarity? I'm also going to provide in class a flowchart which helps to determine polarity as well. So what do we have to do first? Well, we have to write our Lewis structure. Then we also want to identify what our shape is. We use our dipole moment symbols to denote the polarity of each bond. So you're going to go in and calculate the electronegativity differences for each individual bond. There is no sum, there is no multiplying. It just says these two atoms are connected. What is their electronegativity difference? Doesn't matter if you have 4 of the same bond. Each one of those only has one electronegativity difference that's associated with it because only 2 atoms are connected at a time. So if I look at my structure and I have no lone pairs on the central atom and all the bonded atoms are the same, that's going to result in a nonpolar molecule. Why? Because if all my bonded atoms are the same, then that means they all have the same dipole moment between them and they all cancel out. If I have no lone pairs on the central atom, but bonded atoms are different, then I'm going to end up with different dipole moments. They would not cancel out, and I'd have an overall dipole moment, which says I'm polar. When we have lone pairs of electrons on the central atom, typically your molecule is going to be polar. If you have a polar bond, the molecule is going to be polar. Your exceptions to this would be if your shape was linear or square planar. So determining whether the following bonds and molecules are polar or not. So over here we have our bonds. So this is literally just looking at what is my electronegativity difference between these two things. I subtract, and then I look back to my scale. So silicon and chlorine, 1.8, 3.0, electronegativity difference of 1.2. That tells me that I am polar. The difference between carbon and hydrogen, 2.5 and 2.1, is 0.4, nonpolar. Carbon and itself, well, anything from itself is 0, so this is a 100% nonpolar bond because the difference is 0. And then potassium and fluorine. Potassium is 0.8, fluorine is 4.0, so the difference there is 3.2. This then is ionic. So in looking at figuring out whether or not molecules are polar or not, once again, my suggestion would be push pause in the video and draw out these structures and determine their shapes. Once you've done that, come back and check to see if your answers are correct. So in selenium difluoride, we end up with selenium's the central atom with 2 lone pairs of electrons and 2 bonded pairs of electrons to fluorine. The overall shape then is bent. When I look, I have lone pairs of electrons. My difference between fluorine and selenium is 1.6, so I have polar bonds. Lone pair of electrons on the central atom with polar bonds results in a polar molecule. Sulfur tetrachloride. So sulfur is my central atom. I draw out my Lewis structure. I see that sulfur has a lone pair of electrons and 4 bonded pairs of electrons, 4 bonds to each of those chlorine atoms. So then when I do my shape, I have 4 bonds, 1 lone pair. That gives me a total of 5, and then I end up with a T-shaped. No, seesaw. So lone pairs of electrons here are going to result then, I look down here, the difference between sulfur and chlorine is 0.5, so these are all polar bonds. Lone pair of electrons on sulfur says, I'm going to be a polar molecule. Polar bonds, lone pair on the central atom equals a polar molecule. All right, down here, carbon is going to be my central atom, even though I have 2 here that are all alone. Why? Because hydrogen can only make 1 bond. So carbon goes in the middle. It makes a single bond between hydrogen and each of the chlorines. So I have 4 bonded pairs of electrons to my central atom. Carbon has no lone pairs, so my shape would be tetrahedral. I have no lone pairs of electrons. However, my atoms are not the same. I note between carbon and chlorine, that is a polar bond. So this molecule is going to be polar because I have a central atom with no lone pairs of electrons with 4 different atoms bonded to it. Or I should say 3 of the same and 1 is different. Carbon dioxide. We've looked at this structure before, and it is carbon that is double bonded to each of these oxygens. There are no lone pairs on the central atom. My shape is linear. My shape is linear here, and I have the same atoms bonded to carbon with no lone pairs. So even though that the electronegativity difference between carbon and oxygen is 1, it tells me I have a polar bond. Because the shape is linear, the tug of war cancels out, nobody wins, and then this molecule overall is nonpolar. So, process that we follow. We draw our Lewis structure, we assign our shape, we look at our bonds as to whether they're polar or not, and then we look back to our shape and say, do I have lone pairs of electrons on the central atom? If I do, more oftentimes than not, the molecule is polar. If I don't have lone pairs of electrons and everything that's bonded is the same, it's going to be nonpolar. If things are different, it's going to be polar.